We've learned all of the different ways that we might factor a polynomial, and this lesson will sort of put it all together. So this is on factoring completely. And in factoring completely, we're going to use all of those skills that we've just learned, but we're often going to have to repeat the process. So the general rule is to first factor out a GCF, which means if every single term that you have, no matter how many you have a factor that you could take out, you should take it out and pull it to the front of your polynomial. The next thing I'm going to do is count how many terms that I have to help me determine which method I would use to factor. So if it has 2 terms, we have talked about the difference of squares pattern, the sum of cubes pattern, or the difference of cubes pattern. If there's 3 terms, it might be a perfect square trinomial. I might just be looking for factors of C that add or subtract to B. That's when A is 1. Or if A is greater than 1, I might have to do my tic-tac-toe factoring. If I have 4 terms, I'm going to factor by grouping. And then I'm going to repeat that process if I have any factors that have a degree greater than 1. So if I go through all of that and I still have an x squared or an x to the third, I'm going to start back at step 2. If you are in my online class or residential class at Bellevue University, there should be a nice handout for you that goes into much greater detail on each of these things, just as a reminder for how to factor completely. So for our first example, the first thing I'm going to do is take out a GCF because I can take a 6 out of everything. So I'm going to pull the 6 to the front. That leaves me with x squared minus x minus 6. Now, I still have an x squared, so that tells me it's possible I'm not done. I have an a value of 1, so I'm looking for numbers that multiply to c that subtract. So multiply to 6 that subtract to negative 1. So numbers that multiply to 6 are 1 and 6, or 2 and 3. I need them to have a difference of negative 1, so I'm going to use positive 2 and negative 3. So that's 6, and then x plus 2, x minus 3. Because this is x to the first and this is x to the first, I know that I'm done. On my next example, I have 2 terms and they're being subtracted. It's not a cube, but it could be a difference of squares pattern. So even though this is the 4th, the question is, can I take the square root? So the square root of 1 is 1, and the square root of 16x to the 4th is 4x squared. So this does fit the pattern because it's being subtracted and they're both perfect squares. So now I'm going to write it as 1 plus 4x squared and 1 minus 4x squared. I have 2 binomials, but notice each of those binomials has an x to the second. So it's possible I'm not done. So I go back to my list and think, okay, I have 2 terms. For this first binomial, I have 2 terms that are both perfect squares, but they're being added. I can't do anything more with my first binomial. However, on my second binomial, 1 is a perfect square with a square root of 1, and 4x squared is a perfect square with the square root of 2x, and they're being subtracted. So I get to use difference of squares pattern twice. Notice my first binomial just comes straight down. I didn't do anything to it, but this binomial breaks into 1 plus 2x and 1 minus 2x. I've already checked this one. I know it doesn't break down further. So even though it's possible to have 4 binomials, my final answer will have 3. Here's another one. I have 2 terms and they have a GCF of 10. So I will take a 10 out and write what's left, which is 8w cubed minus 1. Notice this is a cubed problem, so I'm going to look at my difference of cubes pattern and see if it fits. The cubed root of 8w cubed is 2w, and the cubed root of 1 is 1, and they're being subtracted. So that pattern says take a, let's go ahead and label these a and b, a minus b, and then a squared plus a times b plus b squared. So that is my final solution. This one has 4 terms. Again, I would first check every term to see if there's a GCF. In this case, there is no GCF. However, I can break it down into 2 parts with a minus in between. I'm going to take a GCF out of my first two terms. I'm going to take out an x squared. So I'm going to write that as an x squared on the outside and then x minus 5 on the inside. Here I'm going to take out because there's really no GCF, I'm going to take out a negative 1. A negative 1, so I divide both of these by negative 1. Negative x divided by negative 1 is positive x, and 5 divided by negative 1 is negative 5. Now I see that I have a common factor of x minus 5. So I'm going to divide both of those by x minus 5. And when I do that, I move that x minus 5 out front. And what I have left is x squared and minus 1. Again, I have a binomial that has a degree greater than 1, so that I always check that to see if it can break down further. This happens to be two perfect squares being subtracted. The square root of x squared is x. The square root of 1 is 1. So this binomial breaks down into x plus 1 and x minus 1, and I already had an x minus 5. So again, I could have had 3 binomials, and in this case, I did. Try this one. It is very difficult. Get as far as you can, then press play to see how you did. My first attempt on this one would be to look for numbers that multiplied to 27 that subtracted to 26. So numbers that multiply to 27 that subtracted to 26 are 1 and 27. But this 6th power and 3rd power can kind of throw us off. So think about it this way. If I had x squared minus 26x minus 27, I could factor this fairly easily into x minus 27, which we would have found here, and x plus 1. This is the same idea, except instead of x, we're going to say, what if u was x cubed? Well, couldn't this be u squared minus 26 times u, because I've replaced it with the x cubed, minus 27? So isn't this just u minus 27 and u plus 1? Oops. And now I'm going to put that x cubed back in for u, so now it's x cubed minus 27 and x cubed plus 1. So this is using a method called u substitution. It's one way to think about it. But again, no matter what, this is the pattern that I'm looking for. But I see that I have a possible 6 binomials, and right now I only have 2 written down. So I have to see what's left. Looking at this first binomial, I see that this is a perfect cube with a cube root of x and a perfect cube with a cube root of 3 being subtracted. So the first binomial breaks into x minus 3 and then x squared plus 3x plus 9. My second binomial is a perfect cube with a cube root of x and a cube root of 1 being added, and so that one breaks into x plus 1 and then x squared minus x plus 1. And that is my final solution. So a lot going on in that question.